In the shadow of Geneva, beneath the Earth's surface, lies a marvel of human ingenuity and a potential harbinger of doom. The Large Hadron Collider is a beacon of scientific exploration, allowing scientists to peer into the subatomic world and finally leading to the discovery of the enigmatic God particle years ago. But now, renowned physicist Brian Cox has recently made a chilling announcement that sent shockwaves throughout the scientific community. Something alarming has been detected at CERN, something that could have consequences far beyond our understanding. Has our quest for knowledge set us on a collision course with catastrophe? Join us as we delve into the abyss of this scientific enigma. But before we dive into the announcement, it is important to understand what particle accelerators are. The Large Hadron Collider, or the LHC, is a 17-mile ring of superconducting magnets and the world's largest and most powerful particle accelerator. Operated by CERN, or the European Organization for Nuclear Research, it represents the pinnacle of human scientific achievement. In fact, it is so powerful that it can recreate the very conditions of the universe's birth. But could this machine, designed to unlock the secrets of the universe, hold the key to something far more ominous? CERN, founded in 1954, is one of the world's most prestigious research organizations. With 23 member states and thousands of scientists, it's a hub for collaboration and innovation. The LHC is CERN's flagship project, but it's just one part of a vast network of accelerators and experiments. Imagine a racetrack, but not for cars or horses. This track is for subatomic particles, and it's a race against time and space itself. The LHC accelerates protons to nearly the speed of light, sending them on a collision course that mimics the energy of the universe at the time of the Big Bang. The protons travel at nearly the speed of light, completing over 11,000 laps of the ring every second. These collisions create temperatures 1,000,000 times hotter than the core of the sun. Thousands of magnets guide the protons on their journey, while intricate cooling systems keep the magnets at temperatures colder than outer space. These include 1232 dipole magnets, which bend the beams, and 392 quadrupole magnets, which focus the beams. Just prior to collision, another type of magnet is used to squeeze the particles closer together to increase the chances of collisions. The task of making them collide is akin to firing two needles 6 miles apart with such precision that they meet halfway. The precision required is mind-boggling, the technology unparalleled. The LHC's design is a marvel of engineering. It consists of two adjacent parallel beamlines that lie hidden 574 feet below the surface, shielded from the Earth's radiation. In this subterranean world, the entire system is cooled to a temperature of -456 degrees Fahrenheit, colder than the vacuum of space itself. This frigid environment is essential for the superconducting magnets to function optimally. The beams inside the LHC are made to collide at 4 locations around the accelerator ring, corresponding to the positions of 4 particle detectors: Atlas, CMS, Alice, and LHCb. Each serves a unique purpose, exploring different aspects of particle physics. Together, they act as colossal cameras, capturing snapshots of these collisions. Scientists then sift through the debris, looking for signs of the elusive Higgs boson, also known as the God particle, and other phenomena, clues to the universe's fundamental building blocks. It's like piecing together a cosmic jigsaw puzzle, one where the pieces are invisible and the picture is unknown. By studying the microcosm, we gain insights into the macrocosm. But with every answer comes a new question, and with every discovery, a new challenge. The LHC is not just a scientific instrument, it's a testament to human curiosity and innovation. It embodies our relentless pursuit of knowledge and our desire to understand the fundamental forces that shape our universe. But as we push the boundaries of what we know, we must also consider the ethical and existential questions that arise. What are the risks of probing the unknown? Could our quest for understanding inadvertently unlock forces we cannot control? In the hallowed halls of CERN, where the boundaries of human understanding are constantly pushed, a revelation has emerged that sends a shiver down the spine of even the most seasoned scientists. Brian Cox, a former researcher at CERN and a voice of authority in the world of particle physics, has recently made an announcement that has left the world both fascinated and fearful. Cox's words resonate with a haunting clarity. The goal of CERN's Large Hadron Collider is to recreate a mini Big Bang. Yes, you heard that right. A miniature version of the very event that gave birth to our universe. The physicist also went on to explain the implications of this goal, highlighting the LHC's extraordinary potential for making new discoveries. This includes its ability to unlock the secrets of the Higgs boson and the exploration of dark matter, a mysterious substance that makes up a significant portion of the universe. Imagine holding the power of creation in your hands, the ability to conjure the very essence of the universe. It's a tantalizing prospect, but one fraught with danger. The mini Big Bang is not just a theoretical concept. It's a tangible reality within the LHC. The temperatures, the pressures, the raw energy all mimic the conditions of the universe's infancy. It's like standing at the dawn of time, witnessing the birth of existence itself. But with such power comes responsibility, and the question looms large. What if something goes wrong? In fact, something did go terribly wrong. Back in 1978, the Russian physicist Anatoly Bugorsky experienced a disaster that would forever alter the course of his life. In 1978, Bugorsky was working on the U-70 synchrotron at the Institute for High Energy Physics in Protvino, Russia. A malfunction led to his head accidentally coming into the direct path of a proton beam. The beam, with a force that defies comprehension, passed through his skull, entering the back of his head and exiting through his nose. Bugorsky's experience was otherworldly. He saw a flash brighter than 1,000 suns, but felt no pain. The beam's path left a trail of destruction, burning through tissue and bone, yet he remained conscious and even walked to the clinic for treatment. The aftermath was both horrifying and fascinating. The beam's path caused localized tissue death, leading to the loss of hearing in one ear and partial facial paralysis. Yet, astonishingly, Bugorsky's intellectual capabilities remained intact, and he continued his scientific career. This incident is not just a personal tragedy, but a cautionary tale that underscores the immense power and potential danger of particle accelerators. The risks of a particle accelerator like the LHC are not to be taken lightly. The potential for unforeseen reactions, the very fabric of space and time being manipulated, these are not the stuff of science fiction, but real concerns voiced by some in the scientific community. The universe's secrets are not just mere toys but instruments of tremendous power. One of the most alarming and captivating concerns associated with the LHC's experiments is the possibility of creating a miniature black hole. Black holes are regions of space-time where gravity is so strong that not even light can escape. They are cosmic vacuum cleaners, the devourers of stars, the enigmatic entities that lurk in the shadows of our universe. The idea that the LHC could create such an entity, even on a microscopic scale, is shocking for the general public and experts alike. Could this black hole grow uncontrollably, swallowing the Earth from within? Those scientists at CERN have assured that any black hole created would be unstable and evaporate almost instantly. The mere possibility has ignited debates, fears, and a sense of awe at the power we wield. It is important to understand how the LHC could create a black hole. It has to do with the fundamental mechanics of particle accelerators. When protons are smashed together at nearly the speed of light, the energy released is so immense that it warps the fabric of space-time itself. Imagine a trampoline stretched taut, and then a heavy weight dropped onto it. The fabric bends, curves, and if the weight is heavy enough, it could create a depression so deep that anything nearby would be drawn into it. That's a simplistic metaphor for what could happen in the LHC. In the world of quantum physics, where the rules of the universe are both bizarre and beautiful, there exists a theory that extra dimensions may be hidden within our reality. If these dimensions exist, the LHC's collisions could tap into them, creating a gravitational funnel that forms a microscopic black hole. This enigmatic dance of particles has even caught the attention of some world-famous scientists, particularly the late Stephen Hawking. In his book Starmus, he warned of a scenario where the Higgs boson could become unstable at very high energy levels. This instability could lead to a catastrophic vacuum decay, a cosmic event that would not only destroy the Earth but the entire universe itself. The esteemed British cosmologist and astrophysicist Sir Martin Rees also expressed his own concerns about the experiments conducted at CERN. In his book, On the Future, Prospects for Humanity, he explored the potential risks associated with particle accelerator experiments, including those at CERN. His words were not merely cautionary, they were tinged with a sense of existential dread. He spoke of a worst-case scenario, where an ill-fated experiment could create a condition called vacuum instability. This instability could, in theory, trigger a phase transition that would ripple through the very fabric of spacetime. The result? A cosmic catastrophe that could engulf the entire universe. Rees's concerns were not limited to theoretical musings. He assigned a probability to these catastrophic outcomes, albeit a low one. But even a minuscule chance, he argued, should give us pause. The stakes are unimaginably high, and the margin for error is razor thin. The scientists at CERN have calculated the probabilities, run the simulations, and examine the theories to argue for the safety of the LHC. In fact, Brian Cox himself acknowledged the importance of responsible exploration, recognizing that there are widespread fears and concerns surrounding the activities of the LHC. But he emphasized that there are rigorous safety measures in place, extensive reviews and protocols that ensure the LHC's operations are conducted with the utmost care. Cox reassured that the energies involved are well within what the Earth naturally encounters, and the chances of creating a stable black hole are astronomically low. Even if one were created, scientists say, it would be so tiny and so unstable that it would evaporate in a flash of energy, a phenomenon predicted by Stephen Hawking known as Hawking radiation. It would be a fleeting moment of cosmic wonder, a glimpse into the abyss, and then gone. Some have gone further, speculating that the LHC's experiments could open a portal to another universe or dimension. This notion, though largely dismissed by the scientific community, has captured the imagination of many and has become a subject of fascination, fear, and even folklore. What lies beyond our reality? Could we inadvertently unleash forces or entities that we do not understand? The idea of opening a portal to hell has even been sensationalized in various media, adding fuel to the fire of uncertainty. But how did this idea come to be, and what does it mean in the context of scientific exploration? The concept of parallel dimensions is not new in physics. String theory, a leading candidate for a unified theory of everything, posits that there may be more than the familiar 3 dimensions of space and 1 of time. These extra dimensions could be compactified or hidden from our perception, but they could theoretically be accessed or revealed under extreme conditions. Now, imagine the LHC as a cosmic key, unlocking doors that have been sealed since the dawn of time. When protons collide at energies never before achieved on Earth, they could, in theory, create ripples or tears in the fabric of spacetime. These tears might open pathways to dimensions beyond our own, like cracks in a cosmic wall that separates us from the unknown. The consequences would be similar as if you were to drop a stone into a perfectly serene lake. The impact creates ripples, waves that spread out, interacting with everything they touch. In the context of the LHC, those ripples could be disturbances in the dimensions themselves, waves that spread out into realms we cannot see or comprehend. Scientists at CERN are quick to point out that the energies required to create such a portal are likely far beyond what the LHC can achieve. The idea of opening a gateway to another dimension remains firmly in the realm of science fiction, but the very fact that we can contemplate such possibilities, that we can explore the boundaries of our understanding and peer into the abyss of the unknown, is a testament to the power of human curiosity and ingenuity. For the scientists at CERN, it ought to serve as a silent warning that some doors, once opened, may reveal truths we are not prepared to face. The LHC's experiments have not only raised scientific and philosophical questions, but legal and ethical ones as well. The very act of recreating the conditions of the universe's birth, of reaching into the primordial soup of existence and stirring it with our technological spoons, has ignited debates that transcend the boundaries of science. Are we playing God? Are we treading on sacred ground, meddling with forces that were once the sole province of the cosmos? These are not merely rhetorical questions, but deeply unsettling inquiries that challenge our very understanding of ethics and responsibility. The creation of a miniature black hole, for instance, is not just a scientific curiosity, but a potential Pandora's box. Imagine a whirlpool, sucking everything into its inescapable grasp, but on a cosmic scale. Some legal scholars and ethicists have questioned whether humanity has the right to take such risks, even in the pursuit of knowledge. Lawsuits have been filed, seeking to halt the LHC's experiments, citing concerns about safety and the potential for catastrophic outcomes. The debates rage on, not just in courtrooms but in the halls of academia, in the media, and around dinner tables. In 2008, a lawsuit was filed in Hawaii by Walter L. Wagner and Luis Sancho, who sought to halt the LHC's operations. They argued that the collider might produce planet-devouring black holes or never-before-seen phenomena that could destroy not only the Earth but the entire universe. The lawsuit demanded a temporary restraining order against CERN, contending that the organization had failed to provide an environmental impact statement as required by U.S. law. Though the case was dismissed, it ignited a firestorm of debate and brought the LHC's potential risks into sharp focus. Across the Atlantic, in Germany, a teacher named Otto Rössler filed a complaint with the European Court of Human Rights, alleging that the LHC violated the right to life guaranteed by the European Convention on Human Rights. Rössler's concerns were rooted in the fear that the LHC could create microscopic black holes that might grow uncontrollably. Although both lawsuits were unsuccessful in the end, they form part of a broader movement of concern and skepticism surrounding the LHC. They reflected a deep-seated anxiety about the unknown, a fear that our pursuit of knowledge might lead us down a path from which there is no return. CERN was formed in the shadowed aftermath of World War II, when the world was still licking its wounds and the echoes of destruction were a haunting reminder of human folly. It was a time when the very fabric of society was torn, and from that chaos, a group of visionary scientists dared to dream. They dreamed of a place where the boundaries of nations would dissolve, where the pursuit of knowledge would be a beacon of hope. They envisioned a laboratory, a crucible where the mysteries of the universe could be explored, where the secrets of existence could be unlocked. Thus, CERN was conceived, a child of war and wisdom, a symbol of what humanity could achieve when driven by curiosity rather than conflict. Over the years, CERN has been at the forefront of particle physics, contributing to our understanding of the fundamental forces and particles that make up the universe. The organization has been involved in numerous groundbreaking discoveries, such as the discovery of neutral currents and the W and Z bosons, particles responsible for the weak nuclear force. The Higgs boson, a particle that gives other particles mass, was a theoretical ghost, a whispered legend in the annals of physics. Its existence was a puzzle that taunted scientists, a riddle wrapped in the very essence of reality. CERN's relentless pursuit of this phantom led to a moment that shook the scientific world. In 2012, the Large Hadron Collider finally unveiled the God particle. It was a triumph of human ingenuity, a testament to our unquenchable thirst for knowledge. But the Higgs boson is not the only enigma being probed by CERN scientists. In an astonishing breakthrough, CERN's LHC has unveiled a particle that defies our conventional understanding of physics, the pentaquark. This particle, as its name suggests, is composed of 5 quarks, including an antiquark. This is a stark departure from the more familiar protons and neutrons, which are composed of 3 quarks each. The existence of such a particle was not anticipated in nature, making its discovery a testament to the unpredictable and often bewildering nature of the quantum world. The discovery of the pentaquark at the Large Hadron Collider in Switzerland has opened up a new frontier in our understanding of the universe. These particles may exist for only 100,000th of a billionth of a second, but their implications could be eternal. They could hold the key to understanding how our universe is formed, how the fundamental particles of matter stick together, and how the strong force, the glue that holds the insides of atoms together, operates. The pentaquark is not alone in its exoticism. Alongside it, scientists have discovered new tetraquarks, particles made up of 4 quarks. These discoveries are not just adding to the particle zoo, they are reshaping our understanding of it. They are allowing scientists to begin grouping these particles together, much like the elements in the periodic table, paving the way for a new theory and set of rules governing this exotic matter. Additionally, in May 2023, CERN's researchers made another significant discovery, the observation of a rare Higgs boson decay into 2 muons. These findings mark a significant step in confirming the properties of the Higgs boson. It's like finding a missing piece in a cosmic jigsaw puzzle, one that helps us understand why things have mass at all. But the mysteries of the universe are far from solved. Just in April, CERN announced the discovery of a new particle, smaller than quarks and leptons. This finding challenges our current understanding of particle physics and opens up a new frontier in the quest to understand the fundamental building blocks of the universe.